Many AI engineers using RAG as their standard, but what if it's not most optimal solution? Today we're going to compare RAG and context caching. We're going to test two queries with Anthropic Claude Sonnet. We're going to compare cost, performance, and accuracy. RAG is a search engine. Every step requires query, search, context retrieval, and generating final response. So as you can imagine, the architecture often is complicated and requires some setup. You would need a vector database, you would need a pipeline which will fill this database with data, which will generate vectors from data, and you will need your model to be able to see data from output. How it's usually working. So first step, usually you set up your data. When you have your data, you need to generate vectorized data and save it in database. It's not every database you can use. It should be a vector database, but also you can use a Postgres with extension which allows you to store vectors in there. When you vectorized your data and saved it in database, your search engine is basically ready. Then when you do a query, first what you do, you search your data in database. When you have result, you feed these results to your model, and then model will use these results to generate a final response. This is usually this optimal solution when you need to have up-to-date data, when you need to have specific data based on your domain, on your business. But sometimes, not often, but sometimes it's over-engineered. For example, when you have, let's say, documents for 100 pages, would you set up RAG for it? I would say no. For smaller documents, for other stuff like not big informational documents, I would actually use context caching. It's a relatively new feature which is now existing in most of models like Google Gemini, ChatGPT model, OpenAI, and Anthropic. In context caching, we send our big document to large language model API, and it saves document in RAM memory, or maybe other quick retrieval memory. Actually, I researched this, and there is not much information on how context caching works under the hood. There is also key caching when they store your context in key value database, but context caching itself, I suppose they store it in RAM, which allows you to quick retrieval, and since you are not often do it, you are not store a lot of documents in context, it might be enough for these purposes. When you store your context in memory, first run will actually take like a big chunk of context, but every next query will not take all the context. You can see when you query with context caching, every next query will use a smaller amount of tokens, and this where context caching beats RAG on smaller documents, but on cases when you have a lot of queries. So I prepared some repository. This repository contains two setups. One is local and one is AWS Lambda setup. Today we're gonna run both of them and compare. Maybe there is some difference because using RAG locally might be some overkill, and let's see how it works with Lambda. So let's see what we got here. Okay, we have some steps. Okay. Let's initialize our virtual environment. Command not found Python. Okay, what the hell? We have Python 3. Okay, now we have this. Now we inside our virtual environment. Let's install some stuff. You may have installed into your global. So we installing some packages. Maybe I can go through them a little bit. This default one, we have some LangChain packages. LangChain is a framework which allows you to build your own AI agent. Here you can see a video of mine about LangChain and LangGraph. So it's done. Let's set up RAG store. So we have first script, set up RAG store. Let me go quickly through it. Yeah. So S3, not S3, we actually use it everything locally, but I've used same code for Lambda, that's why I named it as S3. What we're doing here, we are getting our document company knowledge, and we're gonna use this book as our RAG data for RAG, or our knowledge base. And yeah, here what we do, we actually generate vectors out of our company knowledge, and we create some FAISS files. Since I already did it before, we already have this FAISS index. I can open it. As you can see, it's not readable, but another file is readable actually. So it's you see that it's something like chunks. So we have some, let's say, setup of our local RAG database, which is similar to what you would have on your cloud or on your S3 bucket or in other database types. So let's run our benchmark. First, let me go through benchmark, what it does. First, it takes vector database from local. As you can see, we have it here, FAISS index. Then we search top case 3 results. So we have a query here. We will gonna run 2 queries for each method, RAG and context caching. So we have 2 queries. First query is explain division of labor for pin manufacturing, and second query is how does carriage improve markets. These 2 queries say actually specific to this domain, in this book. So as you can see, we have these words like division of labor and markets and everything. So we search specifically what we have in our knowledge base. And how it works, we put query in our main function called run RAG. First we search results in our vector store. We get top 3K results. Then what we do is we pass these results to a prompt as a context, and we pass question, which is query, and we simply send it to our model. We use in this benchmark Anthropic Claude, and we run it on Amazon Bedrock, but you can use any model which supports Bedrock. You can even use OpenAI API or other API, it doesn't actually matter. And what I wanted to highlight here is that we always get in top 3K results, but they might be not relevant. What you usually do in this case is you set up additional filtering of your results. In that case, that in the end, if results are not relevant, you can actually receive some relevance rate, something like that. And if this rate is very low, you just filter results out, and you should like return empty array or something, which saves you from false result and false context. But in this benchmark, we're not going to do that. We're going to go simply. So let's run benchmark. I hit enter. We have first query. So it's completed in 7:33. RAG query completed in 7 seconds 33. Okay, another query completed in 11 seconds. And here you can see that we have results. It's not a full result because I cut it out in order to not display everything, but yeah, it's working. And what we're gonna see here. So we have our summary. We have RAG. Latency for RAG is 7 seconds. We have prompt cache, and latency is even more, 11 seconds. And as you can see, cache write used a lot of tokens, which is expected because we put all our big document into context. And as you can see, for second query, cache write is null tokens. Cache read is the same amount of tokens which we wrote before. And query took only 11 tokens, So we saved 90% of tokens. And for RAG, we still used 600 tokens for second query because we still passed our full context into message to a model here, as you can see. And let's look at the second method, which using context caching. So here what we do, we generate our context chunk from our full context, which is our document from our full text, and we simply pass it to a model with special parameter called cache control. And this is how we tell that to our model APIs that we want to save this context for caching. And this is how it simply works. And every next query will use only a number of tokens in that query. Unlike RAG, for RAG, every next query will use all the context retrieved from RAG. Yes, it's smaller, it's not 18,000, but it's 600 tokens, sometimes 1,000 tokens, because we pass our search result to K3 search result. So this is result we get. Our RAG on average took 7 seconds, while our context caching benchmark took around 11 seconds. And why would it be so slow? Why would it be slower than RAG? There is an explanation for that. First one is that we run query on a remote model, which is not locally. What we do here, locally we use RAG, which is relatively quick because it's close and it's not very big. So we retrieve our RAG and we send, let's say, not very big. Let's do second benchmark, set up our RAG store on S3 bucket, deploy it, and run it on Lambda. So let's see what we have here. Let's go to README, CDK. Yeah, let me quickly recap what we have. Here I set up some CDK code. Again, I told it before in previous videos, I like CDK. It's way better tool than Terraform. Like, if you are an engineer, if you're a developer, if you like to code, it's very easy to set up your infrastructure with code, not with some YAMLs. And YAMLs in YAMLs. Here it's very good, it's TypeScript, everything typed, it saves you from mistakes, it helps you to find existing resources, it helps you with configuration. Even if you don't know it, you always can look up at types, so you can click it here, you can read what is memory, what is environmental storage, what are the values, what other properties you have. This has helped me so many times with development and increased my speed, and yeah, it's very good tool. Let me quickly recap what we have here. Main stack, it's actually one and only stack. Sorry, I'm not clean coding here. Yeah. First we create bucket, then we do deploy our document to bucket from config. You don't have to do it, you can upload manually from console, but I wanted to just make it everything consistent. What we do here, we create our Bedrock policy to allow our Lambda to use Bedrock with these two actions. So we create Lambda from code. Here I haven't done like usual stuff like Node.js function Lambda because I needed a Docker image specifically for this. Let me show you quickly. So here, as you can see, I also needed some additional requirements to install from layer. Also needed some layer because these specific packages say actually very big and Lambda has a limitation for size, so that's why I needed Docker here. Memory size, I don't know why it's 3 gigabytes. Let's put maybe 4 gigabytes. Yeah, and everything else is pretty default. This Lambda is to set up our RAG store in S3 bucket, and this Lambda is to run benchmark. It also has Bedrock policy, and first one has Bedrock policy, but I don't know why do we need Bedrock here. Ah, yeah, we're using our Bedrock to build vectors. Yes, that's everything correct. And yeah, and we allow our Lambda to read from S3 bucket. And for RAG Lambda, we allow to read and write because we're going to write our fast index. And this is just output. Yeah, so let's deploy everything. It's actually already deployed for me, but I'm going to run it again just to show that it works. Bootstrap I will not run because it's already bootstrapped. We in AWS console. Let's switch to US East where we deployed our function. And here we have two functions which we deployed 2 minutes ago. And let's run first one. We're gonna just run it with test event. which should work. Okay, we just updated the function. Maybe now it will work. As you can see, it's cold run. Lambda has a cold run and hot run. Cold run, it's when it's basically initializes this function, kind of starting container, but hot run is when container is already running, and just same Lambda receives new event, a new request, like that. Cool, our RAG setup is finished. Let's check S3 bucket. Oh, nothing is here. Ooh. Okay, let's go here. Cool, we have our FAISS index and we have both files. That's cool, now we're ready to run benchmark. Let's go to run benchmark function. This could be relatively slower because we have low memory. I figured out why we cannot increase memory here, because I have Lambda functions in another region and I'm not using this account very often, and AWS has some limitations to memory, Lambda memory, when you use it in multiple regions for the first time, which is very strange, but okay, I can get it. Let's click test. It's gonna take some time, and we have our first error. Cool. Parameter validation error. Let's try our test again on Lambda. It's running. Let's wait for a few seconds. Cool, we have our results finally. And let's see what we have here. RAG latency is around 7 seconds, and cache latency, both cold and hot, still 10 seconds, which is higher than RAG. Also, yeah, we have tokens. RAG, same, using 600 tokens, cache read and cache write, kind of similar. So we have almost same results as locally, and what we can see here is that RAG is quicker, more performant, but when you're going to run a lot of queries for the same context, for the same RAG, context caching in that case will be cheaper. This leads to a breakpoint set after, with our data, of course, after around 104th query, context caching will be cheaper. I would say this data is just sample data. On other variants of data, we'll have different results, but the main summary here is following: that context caching usually slower, might be same time. It might be cheaper with small documents, but when you run a lot of queries, and it's definitely cheaper in development cost, because you're not spending time on setting up RAG database, setting up pipeline to create data for RAG database. You're not setting up complex infrastructure. You just use existing model. You use context caching as built-in model feature, and that's it. And so if your app has high traffic, a lot of queries to your custom large language model or custom assistant, custom GenAI assistant, and you don't have like big knowledge base, you might consider using context caching. In other cases where you have like more complex application, when you need some custom pipelines, when you have big knowledge base, in that case I would advise using RAG. Like I said, per query cost is cheaper with context caching, but initial query cost is much more higher, because you need to send your full context, which usually you don't need to send this big context when you use RAG. You just retrieve specific information, top K results from your RAG database, and then you use it for your LLM query. Here in context caching, it's cheaper per query, but it's higher with initial cold start cold sending. So consider using context caching when you have a lot of queries on the same context. Maybe you have some kind of multiple assistants, each assistant has its own context caching, something like that. To summarize, what is the best choice for you? Here what we have. You want to use RAG when you have big, massive scale of data, terabytes, gigabytes, or terabytes of data, even hundreds or thousands of megabytes, because as we know, current context limit is not very high, around 1 million for Gemini, and a little bit smaller for ChatGPT by the time I record this video. And Yeah, caching is costly to use at scale. Use context caching when you have a lot of queries, when you have high volume of traffic for the same assistant. Then you might want to use context caching. When you have small data, maybe you have some changing data. Yeah, and for large initial cold run cost, still consider amount of data you have. So it's always a trade-off. In every architecture, even in AI architecture, you need to think about trade-offs. So always use what's best for your solution, what's best for your product. Don't use something which is on hype, something popular. Don't use a solution only because it's popular. Always think about what's best for your product. Think about requirements, functional, non-functional requirements. Think about short term, long term, what will be best. Maybe in half a year your rack won't be needed for you, or maybe context will grow. Maybe it's okay to overpay for now and build your rack later. So that's what I'm going to advise. All the code which we seen here going to be in description. As always, hit like, subscribe, and see you in next video.